Welcome to the Shikasa Boo Motor channel. This channel provides easy-to-understand explanations of car mechanisms. Mazda offered the MX-30 with 3 different powertrains. A 2.0-liter naturally aspirated inline-4 engine with a BSG mild hybrid system, paired with a 6-speed automatic transmission. A pure battery EV equipped with a relatively small 35.5 kWh battery. And a plug-in hybrid using a 0.83-liter naturally aspirated rotary engine. Although the MX-30 was launched globally starting in Europe in 2020, it has since disappeared from many markets and is now sold in only a handful of markets. Unfortunately, it failed to achieve commercial success. There are 3 main reasons for this. The first is the unconventional body layout, characterized by rear-hinged rear doors. One has to wonder, what kind of customers Mazda thought would want such an inconvenient door design? It might be a different story if it offered truly stunning styling in return for that inconvenience, but the second is its status as a pure battery EV with an underwhelming battery capacity. Its battery, at just 35.5 kWh, allows for a driving range of only around 200 km per charge. The Volkswagen ID.4, launched in the same year, was offered with either a 52 kWh or 77 kWh battery. A year earlier, the Peugeot E208 was released with a 50 kWh battery, while the Volvo XC40 Recharge came equipped with a 78 kWh battery. The thinking that battery EVs are not well suited to highway driving and should be tailored for short-distance transportation with smaller batteries did make sense in theory. It made sense in theory, but it simply didn't appeal to consumers. The third is a plug-in hybrid paired with a rotary engine that makes little sense. In this video, we explore why hybrid systems and rotary engines are a poor match. Rotary engines used to mean Mazda, and Mazda used to mean rotary engines. Since their debut in the Cosmo Sport in 1967, rotary engines were primarily used in sports cars, including the RX-3, the 3 generations of the RX-7, and the RX-8, and were produced until 2012. A rotary engine mainly consists of the following components: rotor housing, rotor, eccentric shaft, and stationary gear. The eccentric shaft is the engine's output shaft, and corresponds to the crankshaft in a reciprocating engine. The stationary gear is fixed to the side housing, and does not rotate. Intake and exhaust are routed through either the side housings or the rotor housing. Until the RX-8, all rotary engines were 2-rotor designs, with the 2 rotors mounted 180 degrees out of phase. The rotor moves in an eccentric orbit around the eccentric shaft, while also rotating about its own axis. The inner surface of the rotor housing and the rotor apexes form the combustion chambers, which repeatedly go through the intake, compression, combustion, and exhaust cycles. For every 1 revolution of the rotor, the eccentric shaft rotates 3 times. Because 1 rotor forms 3 combustion chambers, there are 3 combustion strokes per rotor revolution. With 3 engine revolutions per rotor revolution, the engine has 1 combustion stroke per revolution. With a 2-rotor configuration, there are 2 combustion strokes per engine revolution, so the ignition interval is the same as that of a 4-cylinder reciprocating engine. We will look at 3 advantages of the rotary engine. First, it has a small number of components, making it lightweight and extremely compact. This diagram illustrates where the 13B engine is mounted in the RX-8. Because of its compactness, the engine is mounted entirely behind the front axle. Mazda referred to this as a front midship layout. The second is that, unlike a reciprocating engine, it has no parts that move back and forth, resulting in low vibration and smooth rotation. To suppress vibrations caused by the rotor's eccentric rotation, the eccentric shaft is equipped with counterweights phased 180 degrees apart. The third is its high power output. We will compare a two-rotor engine with a chamber volume of 600 cc to a four-cylinder reciprocating engine with a total displacement of 1,200 cc. In a rotary engine, when the rotor turns 120 degrees and the engine completes one revolution, 600 cc of air is drawn in. Therefore, when the rotor completes one full rotation and the engine rotates 3 times, 1,800 cc of air is drawn in. In a two-rotor engine, a total of 3,600 cc of air is drawn in over 3 revolutions of the engine. This shows that the amount of intake air per engine revolution is 1,200 cc. In a reciprocating engine, a 180-degree rotation of the crankshaft draws 300 cc of air into a single cylinder. Therefore, when the crankshaft rotates 720 degrees and the engine completes 2 revolutions, a total of 1,200 cc of air is drawn in. In other words, the amount of intake air per engine revolution is 600 cc. Thus, in theory, a rotary engine can draw in twice as much air as a reciprocating engine of the same displacement. For this reason, a rotary engine can produce higher power than a reciprocating engine of the same displacement. Since the intake air volume is doubled, a rotary engine ought to deliver twice the power of a reciprocating engine. But the real world is not so forgiving. The rotary engine's biggest disadvantage is its low thermal efficiency, leading to poor fuel economy. In order to improve thermal efficiency, heat losses must be reduced. Heat loss is the phenomenon in which energy that would ideally drive the engine is released as heat from the engine cooling system and into the atmosphere. To mitigate this effect, reciprocating engines narrow the valve-included angle, reducing the combustion chamber surface area, and thus limiting heat loss to the cylinder head. In DOHC engines of the 1960s, valve-included angles of around 40 degrees were common, whereas modern high-efficiency engines typically feature angles of around 20 degrees. By contrast, the rotary engine's design leads to a flattened combustion chamber, which has a considerably larger surface area compared with that of a reciprocating engine. As a result, a large amount of thermal energy escapes to the rotor housing, reducing thermal efficiency. To make matters worse, because the combustion chamber itself moves, the hot combustion gases continually lose heat to the cooler rotor housing. In addition, this combustion chamber shape requires a long time for the flame initiated by the spark plug to propagate. As a result, the engine is more prone to knocking, which prevents the adoption of a high compression ratio. Let's compare its compression ratio with those of other engines from the same era. The RX-813B MSP engine has a markedly low compression ratio compared with Porsche and Honda sports cars, and it is even lower than that of Mazda's other mass-production passenger car engines. A rotary engine draws in twice as much air as a reciprocating engine of the same displacement, and injects twice as much fuel. However, for the reasons discussed above, it does not deliver twice the power, and also suffers from poor fuel economy. Moreover, these negative characteristics are more pronounced at low engine speeds, resulting in limited low RPM torque. This graph shows the engine performance curves of the RX-8 and the Toyota GR86, which is equipped with a 2.4-liter reciprocating engine. Although the two engines were developed 18 years apart, making this an unfair comparison, please focus on the differences in their torque curve shapes. The MX-30 REV uses a series hybrid system. The engine is dedicated solely to driving the generator and has no mechanical connection to the wheels. Therefore, the engine is not involved in propelling the vehicle. When the battery charge is sufficient, the vehicle operates in EV mode, supplying power from the battery to the electric motor. When the battery charge falls below a certain level, the system switches to hybrid mode, in which the engine drives the generator and the generated electricity is supplied to the electric motor. Since the engine can be run predominantly in its high-efficiency operating range irrespective of vehicle speed, fuel efficiency is improved. The newly developed 8 cph engine is a single rotor unit with a displacement of 0.83 liters. It produces a maximum output of 53 kilowatts and a maximum torque of 112 newton meters. The compression ratio is 11.9 to 1, representing a significant improvement over the RX-8's 13B MSP engine. According to Mazda's documentation, this improvement results from high EGR rates, suggesting that the engine is designed to prioritize efficiency over maximum power. Let us summarize the characteristics of the rotary engine, explained in the previous section. The advantages include lightweight, compactness, low vibration, and high output. Its disadvantages are a lack of low-speed torque and poor fuel economy. These characteristics are ideally suited to sports cars. So, how about hybrid vehicles, where fuel efficiency is the top priority? Being lightweight is certainly an advantage. Regardless of the type of vehicle, having a lightweight engine offers nothing but benefits. What about compactness? In Japan, Honda's minivans adopt a series parallel hybrid system combining a 2.0-liter inline-4 engine with 2 electric motors, similar to the one used in the MX-30. The MX-30 has an overall width of 1,975 millimeters, while Honda's minivan is 1,970 millimeters wide. This means that the MX-30 should also be able to accommodate a 4-cylinder reciprocating engine and a hybrid unit. In other words, the MX-30 does not require the compactness of a rotary engine. What about low vibration? These days, even 3-cylinder engines do not produce vibration strong enough to cause discomfort for the driver. What's more, at traffic lights, where vibration is most noticeable, the engine in a hybrid vehicle is stopped anyway. What about high output? Needless to say, high output is not required for hybrid vehicles. What about the lack of low-speed torque? In a series hybrid system, the engine is not involved in propelling the vehicle. Since the engine is dedicated to generator drive, it operates in an efficient 2,300 to 4,500 revolutions per minute range to reduce fuel consumption. Therefore, a lack of low-speed torque is unlikely to be a disadvantage. What about poor fuel economy? This is a fatal flaw. Let us compare it with other plug-in hybrid vehicles. Note that all figures in the table are for the Japanese market models. This is no joke. The rotary hybrid MX-30 actually has poorer fuel economy than the non-hybrid MX-30 equipped with a 2.0-liter engine. Why on earth did Mazda choose a rotary engine, which is inherently ill-suited to hybrid applications? Mazda likely initially envisioned this model as a battery EV equipped with a range extender. Battery EVs are best suited to short-distance use, and long trips should only be undertaken occasionally. Since long trips are only undertaken rarely, customers would probably not be too concerned even if the hybrid mode consumes somewhat more gasoline. Then this would be the moment to bring back Mazda's iconic rotary engine. Such thinking could be glimpsed in Mazda's messaging at the time. However, no market existed for such a car. Moreover, during the development of the system, competitors' technologies continued to advance, and the driving range of battery EVs kept increasing. In short, Mazda misread the direction in which the world was heading. That said, Mazda should not be blamed. Mercedes-Benz, Audi, Volkswagen, Porsche, Stellantis, Volvo, GM, Ford, Honda, and Nissan all misread the situation. After all, no one can truly know the future. Thank you for watching. If you enjoyed this video, please consider subscribing to the channel. We'll see you in the next video.